Good afternoon, everyone. Just wanted to point something out from yesterday. When we were doing, actually it was, and we were finding the Fourier spectrum. This one, it's really easy or really hard depending on how you go about it, right? If you do the integral, right, and do the ANs and the BNs, actually turns into a rather difficult integral if you're trying to get a generic solution for it. You can use SymPy to evaluate each harmonic, and if you do it right, you'll either get the right value or you'll get zero, but it won't tell you generically. Really the best way is to use this transform where this equals 0.5 minus 0.5 cosine 2 times 2 pi ft. Now, let's just remember, xt can be represented with a naught plus the sum of infinite cosines to and a sum of infinite sines. Right? Well, this is already in that format, except it's just not infinite, it's finite. A naught is right there. This is a cosine, right? And so that's got to be a, or you'd think it's A1, right? It's just, if this is the fundamental frequency here, well, when we did the identity, we ended up with an extra 2 here, right? So in fact, it's A2, right? So if you're trying to mathematically check your work on that one rather than do the estimation way, right? It's really just a lot better to use this trig thing. And yep, I had wanted to make this great example and I just ran into the wall, not realizing, of course, just how easy, or I knew it was easy in that everybody kind of knows that when you multiply a sine, square a sine or a cosine, you kind of double the frequency and you get a DC offset. But I'd wanted to prove it, and it's just it's too hard. Any questions on that? All right. So today, we're going to talk about mass, springs, and dampers, all right? And mass, we're just going to draw with a box and the word M, or the letter M. Spring, we're just going to draw like a spring, and a damper. This is the symbol for a damper. Now, if we look at velocities, all right, the velocity of that mass, which is and velocities of like a moving surface, we can change those into a voltage, right? And if we do that, we can turn a mass into a capacitor. We can turn a spring into an inductor, and we can turn a damper into a resistor. All right. Now, mass, I think we're pretty familiar with. In fact, this mass, spring, and damper systems, right, you probably have seen in differential equations where I can have some kind of surface that's going to move, right? And I can have a damper connected to a spring connected to a mass. And the thing is, yep, we spend, while we do spend a lot of time with op amps and, pure electricity, right? A lot of the things that what are these op amps sensing? What are the microcontrollers and the FPGAs you're doing in 118 controlling? Some physical system, right? And physical systems have mass, spring, and damper, all right? And this is my drawing of a hard disk, right? And it's spinning around very fast. And you have a control arm that's trying to position itself to know where to read things, right? It's got to be really accurate. But this is really moving back and forth. And if you've seen them, they move back and forth like that, right? So, the rod has an effective mass, and the bearings that it's in and the pistons driving it, they have, a resistance to movement, which is like a damper. And then the arm itself, right, can have a springiness to it. So while the microcontroller is telling this what to do and where to go, right, the head of that mass, where it will go where you want it to go, but it can, right, oscillate back and forth until it finds its position, right? You want it to be able to move to the correct position as quickly as possible, but not overshoot, right? And so you can, once you know all these things effectively, right, then you can create a system model for it. And then you can use KCL, KVL, Laplace, Fourier, everything we've learned so far, you can use to model that system, right? Even LT spice we can use to model mass spring and damper systems. All right. And I think that'll be enough of an example for now. Although while I was talking to you, no, I'll have to find it for you later. But basically, people play music through the hard drive controller, and it makes a sound, and you can see it. It's a horrible music thing, but kind of gets the point across. How do you find? Oh, so, hey Andrew, sorry, I just saw your question there. How do you find the generic AN? Sorry, everybody. I didn't see that question. So in this case, you don't, because this transforms into this identity. There is only one term, and it's doubled. The frequency is doubled, and now you have a DC offset. But there are no sum of signs. So there's nothing generic about it. There's only one there, right? There's only one frequency created, and it's double the original frequency. All right. Did that help you out, Andrew? Right. And so some problems, I mean, that's the complete answer. You could call it generic, but okay. A 50% duty cycle square wave, it does have an infinite series. So there is a generic thing, right? Like I was telling you the other day, there's Bn equals 2n pi, right? And the ANs for a 50% were just equal to 0, right? So that's the generic form of it, all right? Triangle waves, right? Things that start off sine waves, right? Generally, if it's a sine wave or a cosine, there is only one frequency. So this expansion, if you will, is the whole thing. It doesn't need to be generic. So this saying that this is the final answer, Riyadh? Well, no, because you're supposed to kind of do it in an intuitive manner rather than do it this way. But whenever I do anything, I always try to do it more than one way. That way I check my work. That way I can prevent mistakes. All right. And yeah, on that homework, if I'm telling you to do it a particular way, you really got to do it that particular way, because on an exam, if I'm telling you to do it a particular way, it's because I'm trying to test something, okay? And if I'm trying to test whether you really know what's going on or whether you can look up a trig identity, I'd rather see you do it the intuitive way. But again, always be checking. Sure. Sure, Andrew. If there is no generic solution, just say it. Okay. But yeah, just say it. All righty. So I thought I put so this link, it's in Canvas. All right. So you have everything that's here. All right. So that's like the big picture. So let's just try to talk about what's going on, right? So springs, when you compress or move them away from their natural position, right? Or masses that are moving, right? They both store energy in different ways, right? And inductors, they store energy by moving charge, right? Capacitors, right? It's a charge difference, right? A pendulum actually has two kinds of energy, right? It has potential energy and kinetic energy, right? Other energy storage devices are a spinning flywheel, right? Get that mass spinning up and you can store energy, right? So these systems, right, because they have, with one spring and one mass, they have two different ways of storing energy. And so that means you can model it with a second order differential equation. And it'll be one inductor and one capacitor, right? And you could think of it as one potential and one kinetic energy, right? So again, spring mass damper systems as RLC, they've got to be linear, right? So you can use your Laplace, all of that, right? And not only that, but these systems act like filters. So again, I've kind of talked about this example already. It's just enough for you to know that this is, a real world application. All right. Now, where does it come from? So the force on the mass, right? And the force on the spring and the force on the damper, right? You can see that the capacitor, the spring, the inductor, and the mass, right, in their equations, they all have integration or differentiation, which means they're an energy storage element, right? Or they're a memory element, because in order to integrate or take the or differentiate, you need 2 points in time. Yes, differentiation, when you're finding the derivative at a particular value, right, the delta t goes to infinitely small, but really, if time doesn't progress, you can't see an area increase or go down, and you can't see a signal go up or down. Right. Now, I'll leave it at that. So the kinds of problems, right, is you're going to see is a system diagram. And the thing is it looks like it's got like space or takes up a volume or two-dimensionally, but really that mass is a point mass. I've only drawn it big enough to connect everything up. It's just like a capacitor, right? If you in LT Spice connect a capacitor to an inductor with a long wire, it doesn't really matter. In Spice, wires actually don't even exist. You're just connecting nodes, right? That's called a compact model. Same with the spring and the damper. A real spring, of course, has volume. A real damper has, takes up physical space. But what we'll have is a moving platform, right? That's the input. And it will be connected to a, like a spring and a damper, and then connected to the mass. But you shouldn't think of this as a two-dimensional problem. Really, the damper and the spring are kind of superimposed on each other. It's not like part of this will tip up higher than the other. These are all moving together. And then we have a spring and a damper in series. Now, there is like a procedure to follow, right? The thing, but I warn you, right? You kind of need to know this procedure very well for the exam. Yeah, you could use this as your note sheet, but if you're trying to remember how to do this problem during the exam, you're probably going to run out of time. Okay, but let's just go over the procedure. Anywhere you see a mass, you turn it into a capacitor. Wherever you see a spring, you turn it into an inductor. And there's an equation. So if you take the spring constant and take the inverse, that becomes the inductance. The mass is straight equal to the capacitance. And the damping coefficient, take the inverse of that and make it a resistor, right? Now, these other rules here, I think we'll just learn by doing some examples, all right? Then you can analyze things in the S domain, right? You can find displacement, essentially position, by multiplying by 1 over S, because that's integration, right? And if you want to find the acceleration, you multiply by S because that's differentiation, right? Then if you want to know what that looks like in the time domain, you just take the inverse Laplace transform, right? If you have a mass, spring, and damper, you can determine, is this system overdamped? Is it critically damped? Is it underdamped, right? If it's a first order filter, first order system, well, then things will change in 5 tau. So let's just start. Any questions before we begin with that? Just let me.
Yes, I got a quick question.
Yeah, sure.
Will we be required to calculate things like acceleration or displacement on the exam?
I have it in the past. What it seemed, so rather than calculate, what is the acceleration, what is the displacement, which, yeah, you'd want to know, does the acceleration exceed, the acceleration for which my head implodes or something? That's certainly a problem. I don't know, maybe this time I will, now that you mention it. But what I tend to want to see is, can you get a picture like this, and can you draw the equivalent circuit, right? And then once you have the equivalent circuit, can you come up with a transfer function? And then once you have the transfer function, can you tell me, is it over, under, or critically damped? Right. Also, another question is, once you've done all that, what if the system ages and this damper, right, that damping coefficient changes? What happens? What if this damping coefficient turns in, the damper freezes, right, and it becomes a rod? What happens, right? What if that damper basically doesn't damp at all, right? What happens to the system? Those are the things I'm more going for. But I do have examples, and in the book, right, they, like for an elevator, you start the elevator and you're finding how far it will go. But to me, that would be the next logical step if we were doing a robotics course. Okay. But I'm trying to reinforce transfer functions and over, under, critically damped, but just giving a different way of looking at it. Okay.
Just one more quick, guys, one more quick question.
Sure.
Yeah, I actually looked over this PDF beforehand, and I actually can kind of make sense of essentially the circuit and the transfer function. But will you show us an example of how to tell whether it's over, critically, or under damped? Because I'm still a little foggy there.
Okay, sure.
Yeah, thank you.
I mean, and if it's getting towards 4:05 and I have not done that, just try to get my attention. Okay.
Can do.
Okay. All right. We should be able to do that though. All right. So we have, in this case, we have a moving platform, and suspended is a mass and a damper. So Vx is the input. All right. That's what we're driving. And that Vx, that velocity, becomes the voltage, right? So whatever is the moving platform, right, or that is being moved somehow, that'll be the input, all right? And then Vy would be the mass. Now, here's the thing. While dampers and springs have velocities as well, we really don't care, because the mass is like the thing that's actually being moved, right? That's the person, that's the head, that's the robot, right? So we want the mass, all right? And in this case, we have a moving platform, that's an input, and a damper is connected to one end of it. Well, dampers are resistors, and it's connected, right? So Vx just becomes a moving platform. Now, you might ask yourself, hey, where's ground? Right? There's no ground in here, right, that you can see. And that's because it's hidden, right? Anytime you draw this, you could just draw a fixed surface that doesn't move, and the velocity is compared to that. So you can't just have a voltage, right? It's got to be a potential drop from some known point, and so ground. So the ground is never drawn unless sometimes a fixed surface is drawn. All right. So you just put in a voltage source, one end is ground and one end is to the resistor. Now, if I put ground to this end of the resistor, right, well, then nothing's going to happen, right? You wouldn't connect the ground to the input of a resistor unless I guess I drew it that way. Okay. Now the mass, right, is connected to one end of the other end of the damper, right? So one end is connected here, and then the other end is connected to the capacitor. And now here is like the tricky part. That capacitor, or that mass, is moving with respect to a fixed surface, right? So the voltage change on this capacitor is relating to the velocity change of this mass compared to a fixed point. And so I have to tie one end of the capacitor to ground because that'll be my fixed point, right? And so if I take this resistor and put it to the other side, right? Meaning well, this is connected right. But if I connect this resistor to ground and that capacitor to ground, well, what's that node doing? Well, it's not connected to anything, right? So you've got to connect one side of that capacitor to ground, right? Now, yes, sometimes the device is in parallel with it and it will connect to ground as well. But you're never going to see that mass is moving. And so there's no connection really because it's just velocity compared to something, right? So anyway, we have ZC, we have ZR, it's voltage division. And there we go. That's our first order equation. And the mass would just equal the capacitance, or the capacitance would equal the mass, and R would equal 1 over the damping coefficient. And there you have it. You could then go plot it in an LT spice. I could put a step in the voltage, which would correspond to a step in the velocity. So the velocity goes from nothing to something, a constant. All right, now let's try it again. So here, the moving platform, we're still on, suspending a mass between that. And I've got two dampers in series, right? So again, Vx becomes a voltage source. Automatically, we tie that to ground and one end is tied to the R. Great. The other end is tied to another resistor. Okay, great. And then one end of that damper is tied to the capacitor, and the capacitor, right, is the mass. The mass velocity is compared to a fixed surface, so it's ground. Now, really, this circuit, really, there's an equivalent to it, and we would just add up R1 and R2. Oh, I see a chat, but I'm going to finish my thought. So really, it's the same thing as before. It's still a first order system, but instead of just one resistance, there's an equivalent resistance for the impedance. And so omega naught is different than previous. Right, so Riyadh, one end of the voltage and one end of the capacitor always have to be tied to ground. Okay. And there's something that your question reminds me of that comes up. So this circuit, where I've just made a loop and then I've tied it to ground like that, is the same circuit as this. All right. LT spice, or when you're doing a schematic, just say these are tied to the same point. Right. If I had and then over here, I put node 1 in LT spice, this would simulate, and it just connects these two without putting a wire there. That way it can actually make things look simpler, right? Of course, you need a physical wire to truly connect it, but in LT Spice or schematics, you can use node names to simplify things so you can see it better. And ground is just a special node name. Okay. So now this is a little bit different. We have a moving platform, right? Connected to a damper, connected to a mass, connected to another damper, and that damper is connected to a fixed surface. All right, so the moving platform is the input again. We just draw that. We have a damper, nothing new. Connected to a mass, nothing new, right? Now, yeah, I've already wired this back in here. I've drawn it a different way. So I've already drawn it to ground, but then suspended from the mass is a damper and a fixed surface. So one end of the damper is connected to the mass, and so you can see that, but this is a fixed surface, right? And so you just connect it all the way through. All right. So again, I would use voltage division, and I have a Z equivalent first of these two in parallel. All right, so then I just work it out, and basically we have R1 in parallel with R2, right? Although they don't look in parallel, do they? But from a timing perspective, they are. And so if you want to find the natural response of a system, right, you short voltage supplies, right? So if this is an input, right, I short it. All right. And then if I wanted to see what would happen, I would put an initial condition on this capacitor, and then it would decay, right? Well, now, right, I have a node here, right? I can go through this resistance to get to that node. I can go through the capacitor to get to that node. I can go through here to get that node. So in fact, I can redraw that like this, and these two resistors, excuse me, are in parallel. So then I can draw one equivalent of these two in parallel. All right. So if you look at it, if you went through this, you'd see that, yes, R1 and R2 are in fact parallel. Although from a timing perspective, right, a time constant perspective. So in this case, you have to be careful. I move the moving platform to in between, right? And then I have a damper being connected to a fixed surface, right? So even though these two resistors look like or dampers look like they're going in opposite directions physically, right? both ends of the damper are connected to the input, right? Now, it's true, I could draw it a different way where the other resistor goes one way, right? And then the other end of that damper is connected to a fixed surface, which is ground. So that's what we're getting, right? Then we're suspending a damper from the moving surface and the mass, right? Mass gets connected to here, all right? So this was kind of like a 98 problem of like, what's the time constant of this circuit? And in this case, the resistance this resistance doesn't come into it. And there's two ways to look at that. So if I put a step here, right, if this is an ideal voltage source, it can supply all the current it needs to through that resistor, and still this node will go to that step voltage, right? And so in fact, you just have the traditional, 1 over RC all right. Now, yeah, if you want to look at it to the natural response, short this. Let me short it more visibly. All right. So now you could think of that resistor in parallel with a wire, right? And so the smallest resistance wins, which in this case is 0. And so then that resistor falls out of the equation. So either way you look at it, that particular one, yeah, this resistor doesn't affect it. Now, if I had a small series resistance here, oh, then it would. Okay. But if that small series resistance was a lot smaller than everything else, you wouldn't be able to see it. Okay. So that's almost every version of an RC spring damper circuit that I can think of. Although I could put the moving platform on the bottom, I could move it on. We could be on frictionless rollers, and so we could be moving back and forth from the side, right? So there's a limited number of problems you can ask with an R and a C, or a spring and a mass. Excuse me, a damper and a mass. Now, let's do a mass and a spring. Now, you should start to think that this might not behave in a normal way, because both of those elements are energy storage elements, and there's no dissipation element in there. So, but anyway, moving platform, that's the input. One end tied to ground. Great. One end of the spring tied to the input. One end of the spring tied to the mass. Great. Capacitor, one end, right? Always tied to ground. All right, voltage division. And we get something that, looks kind of the same, but what's going on here, right? So if I try to find the poles, right, how would I do that? I would use the quadratic equation, right? S squared gives me, the A term is 1. The B term is 0, right? Because there's no S. There's no S to the 1. And then the C term is 1 over LC. So if I put that into the quadratic equation, I get plus or minus J over the square root of 1 over LC. All right. And what that means is it's an oscillator, and it oscillates at that frequency. All right. And would oscillate forever. Now, next time, we're going to call this a system that is out of control, because once you put an input in there, it'll oscillate forever. It never settles to a known value. That would mean it's out of control. A system that's in control can oscillate, right? But it just might take too long for the oscillations to disappear, and that would be out of control. Okay, now we have the moving platform is now on the bottom, right? Now, yeah, I'm probably just making these figures up as I go along. And so now the ground happens to be there, not because I'm trying to trick anybody. It's just that's what I felt like doing that day. So the input is the moving platform, and one end is tied to ground, right? One end is tied to the spring. Okay, that's the inductor. One end is tied to the damper of the spring. Okay, and then the other one is tied to the mass, right? And yeah, it's almost like here's the voltage, here's the inductor, here's the resistor, here's the mass, but then you got to complete the loop by connecting one end of the capacitor to ground. All right, and you can do this a series circuit, right? I have it memorized by now, right? And that's okay if you don't have it memorized by now. But if I needed to find it, I would just use voltage division. Although if I were doing a cheat sheet, I would probably have basic circuits already kind of summarized that then I could go and do or prove that it was what it was on an exam. All right, I'd want it at my fingertips. So for this example, right, so R is 5 milliohms. The inductor is 833 microhenries, and the capacitor is 150. So these aren't standard values that you would find in your kit, but we're simulating a mass damper and a spring, not an RLC circuit. All right, so this is once we solve for everything, that's our transfer function. All right, so now six, eight. All right, so now we need to know over, under, critically damped. All right, and that all has to do with the poles. So really, it's the denominator polynomial we care about. Okay, and really you just find where does ds equal 0, right? That's the definition of a pole. Well, that's just a quadratic, right? So the poles are going to be at minus b to a so b is minus 6, a is 1, 6 squared minus 4 times 1 times 8. So 6 squared is 32, right? And minus 4 times 8 is minus 32. When I subtract these, I'm going to get a positive number. So I'll get a positive. So I have a minus here. And so when I add it, I'll still get a negative number. And when I subtract it, I'll still get a negative number. And that's a conversation for next time about where your poles and zeros are. But let's just, if this is the real axis and this is the imaginary axis, right? To be in control, the poles need to be to the left of the imaginary line, right? So just by knowing that this starts here, right? I know that I'm going to have plus a real number and minus a real number, and they're going to be different. And so I'm going to have two different poles, right? And so that means overdamped. But I actually don't need to just determine whether I'm over or under critically damped. Really, if b squared is greater than 4 AC, it's over, right? There's going to be two poles that are different, and they're going to be real. If b squared equals 4 AC, one repeated real pole, right? So that's, if I have a pole here, right, and I put squared, right, that means there's two of them there, right? Because if this equals that, it's plus 0 minus 0. You get the same number, but there are in fact two of them there. All right. And if b squared is less than 4 AC, well, then you're going to get one pair complex poles. And that's going to be under, that's going to be critically damped. All right. So that's pretty much it. It doesn't, remember, this is like what kind of filter, right? And if I let omega go to 0, I get 8 divided by 8, right? If I let omega go to infinity, it goes towards 0. So it's a low pass filter, right? And I'm going to leave it at that for now. But once you find that denominator, put it into the quadratic. Okay. And the thing is since these problems are all convert into, we don't have a negative resistance, we don't have a negative inductance or a negative capacitance. These will all be to the left of that line. Now, in the previous problem, though, there was no resistor. So that wasn't there. So then this becomes 0, that becomes 0, and then I just have plus or minus the square root of that. And so it's not really, and so I have one pair of imaginary poles, all right? But it's not really damped because that oscillates forever. And so it's not really underdamped, right? It's just oscillating forever. Now, yeah, you could have something, if it oscillates for 10 years, well, that might seem like forever, right? If it oscillates for a day, it might seem forever. if you're testing the shock absorbers on your car, right, or if your car's shocks are shot and you hit a bump and your car is oscillating for a minute or even 30 seconds or even 10 seconds, right? The mechanic might tell you, well, that system's in control because the oscillations stop after a period of time. Yeah, but it's still too long, right? So sometimes there's more of a practical definition of out of control, which is there's not too many oscillations due to underdamped. All right. But in this course, anything to the left of this line will be stable, right? And I'll have some kind of damping to it. Anything on the line is oscillators. Anything to this side will actually turn into exponential increase, right? We've only been dealing with exponential decreases, actually. All right. So now they're in parallel. So I just draw it in parallel, right? Now, this one you might not have seen, or you might not know it off the top of your head, but it will be, right, the parallel version of an RLC circuit, at least for the denominator. And if you can see that by find the natural response, short out that power, right? I can go power supply. I can go through the inductor to get to ground. I can go through the resistor and get to ground. I can go through the capacitor and get to ground. They're all in parallel. So ultimately, it's that parallel structure, 1 over RC, but the omega naught squared is still the same term. Now, yeah, how did I do that? I found these in parallel and then used voltage division. And yeah, what kind of filter is that? Right? We've seen filters that you might have S squared in the numerator. We might have a constant in the numerator. We might have a constant times S in the numerator, right, for band. And we might have S squared plus a constant, which would give us a notch. But now we have S plus a constant, not S squared plus a constant. And so it's not really a named filter per se, but this will at high frequencies go to 0. All right. And if I wanted to know, let me see if I, so the denominator from that slide is that. And so really all I need to know, if B squared is greater than 4AC or 1 over RC squared is greater than 4 divided by LC, it's over. If it's equal, it's critical. And if it's less than, it's underdamped. All right. Now we have another example. Oh, sorry, I saw 2 chats.
Professor,
Uh,
I think I can explain why you're confused.
no, I'm just trying to read the thing. What, let me see. What did I put? Did I get it backwards? Yeah, I meant 36. Sorry about that. So 36 is, and I think I had said it was overdamped, but somehow didn't realize I wrote 32. Okay. Is that what the 36 in the chat? I assume.
Yep.
All right. I can't really see your faces. And so in class, right, I would have written something that, and then I would have gotten these looks that I would have realized I had done something. So, you can kind of break in, because I don't know what it is about my Zoom account, but when somebody does a chat, I don't hear anything. I know other people's accounts, like it'll ping or something. I don't know. Anyway, so now we have a fixed surface and a damper, and we have a moving platform and a spring. So let's start there. Moving platform, Vx, tied to ground. One end to the spring, one end to the inductor. One end of the inductor goes to the mass, and the mass is connected to ground no matter what. But now on the other side of the mass is a resistor, which is tied to a fixed surface, which is the same, thing that isn't moving that the mass velocity is being compared to. And this will have a parallel denominator as well, right? If I short this, you can see that all these elements would be in parallel. Except now the voltage division is the capacitor in parallel with the resistor. And in fact, if you work it all out, you get the low pass equivalent.
Can we go over why the capacitor and the resistor isn't in series again?
But they're not, they're in parallel. So I'm not quite sure what you mean.
Or why is it in parallel again? Because like the mass, how I understand it is like like the back of the moving platform is connected to the inductor, and then the back of the inductor is connected to the front of the mass, and then the back of the mass is connected to the front of the resistor. Or is that a wrong understanding?
Well, there is no front or back. Okay, these are like, it's a point mass, and it really doesn't have any dimension, right? Now, yeah, I'm trying to model the system, and so the real system has those things that you describe, but the mathematical model actually doesn't. And so one end of the mass, I think we can agree, because you're measuring velocity with respect to something else that never changes. And we're calling that a fixed surface, which may or may not be drawn, right? And if I were to draw a rod between these two, that would be the same as drawing a line from here to here and shorting out that capacitor, right? So the mass has a velocity, right? And it's got to be able to move, but it's being measured with respect to a fixed surface. So whenever you draw that capacitor, you put a ground right there. All right. But even though it looks like, and yeah, I've even drawn it. Here's the mass. But notice this end of the resistor doesn't come here, right? It's all the same node. Even though it looks like it's not the same node, right? Because it went through a mass, right? This is the trickiest part, okay? Just so you know. Okay. That's Vx. And I'm going to do the spring. I'm going to do the mass. I'm going to do the damper. Fixed. So you might think, oh, I'll just draw the voltage source. I'll call that Vx. This is a two-terminal device, so I'll draw the two-terminal device right there, and there's my L. This is a two-terminal device, and I'll just draw it. Oop. Sorry, then it goes through the mass, and because it went kind of, it looks like it just connects through the spring, right? Well, then I should just be able to draw the capacitor there. Then I draw the resistor, and then I draw ground, right? Well, this, you're right up until here, and you're right here, but you're wrong here, okay? Because this mass, whatever, there's not a current flowing through it, right? It's got a velocity with respect to ground, right? This, yeah, it's true. That's an input. That's Vx. That's my inductor. And one end is tied to the mass. But I can't really, unless it shows that you're connected to a fixed surface, don't connect anything. I would not connect this inductor to that side because then it's just grounded, right? And now this part of the resistor, right? It doesn't matter. I connect here, 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 anywhere, right? As long as we're going in the same direction, right? That's the resistance. So you see it connects to that node here, and then that goes to, then this goes to ground. All right. But see how it's all, that's all the same node. The Vx here, or Vy, excuse me, right, is the same Vy here, right? That is a solid mass, and we're assuming it doesn't compress or expand or anything. And so that when one end is moving at a velocity, the other end is too, right? So it's the velocity is the node voltage, and nodal voltages are compared to ground, right? Not, it's not like a mesh analysis where you're measuring across the device. All right. But that's, so that's the thing. It's, these are not, And yeah, it's true. If I have the damper like this and the spring like this, right? Yeah. Those are going to be in parallel, however I connect them, whatever's connected there. But a mass is one end is tied to ground no matter what. And then everything else connects to it. Because that voltage represents the velocity of the mass. And kind of like whether I'm on that end or that end. And this thing has no dimensions. It's a dot, right? Does that help?
Yeah, I think so. So it's more has to do with like where the voltages are rather than the positions of the
Well,
components.
the velocity is equal to the voltage, or the voltage is equal to the velocity, or represents the velocity, right?
Hmm.
And while these forces are, it's fine, right, to put them in parallel, the capacitor kind of has to be treated differently. And two, I think there's a force going in the wrong direction in the book, but I just haven't had time to get to the bottom of it.
So, Professor,
Yeah,
so regardless of the position of the mass, it needs to be grounded. That's
right.
okay.
Now, as a trick question, so here's my input. Here's a damper, right? One end is connected to the mass, and I've connected that to ground, but now I have a stiff steel rod connecting these two, right? So that the velocity of this and this fixed surface that doesn't move are coupled. And so I would get this, right? No matter what goes on here, that stiff thing is, that mass isn't going anywhere, right? Now, yeah, a non-trick question is, what if I had a spring that then froze in place? What would happen, right?
So, Professor,
Yes,
so in that, the mass is useless then? The
yeah, the
capacitor is
system,
open?
I mean, unless you're trying to make something that doesn't move, right? Yeah, the mass doesn't move. The system is not, if you don't want something to move, you just leave it there, right? You don't put it on a platform, right? So yeah, you're assuming something has gone wrong, right? That would be the assumption. All right, everybody. I'll let you go. Oh, there's a chat.
Are you gonna ask some backward question? Professor?
I can't quite hear you.
Yeah, are you going to ask some backward question, like backward, from electrical to mechanical?
You were fading in and out. Can you type it in the chat?
Yeah, I say, are you gonna ask some backward question, like we are going from mechanical stuff to electrical stuff? So like you go from electrical to mechanical backward?
No, because we're trying to model the physical system, right? Now, yeah, you could say, let's say, you've heard me say that inductors and capacitors are memory elements, and you've heard me tell you that they are also energy storage elements. So, yeah, if you're trying to store energy inductor-like, well, then you would use a spring. Or you're trying to store energy with a flywheel, or you're trying to store energy with water at the top of a waterfall, right? But strictly speaking, for homework, I'm not going to give you the circuit diagram and then work your way backwards. Okay?
Correct. Yes.
Because the whole point of it is to take a physical system and model as electrical. Like the mechanical engineers aren't right now doing the opposite so that they can understand things better in mass spring and damper and use MATLAB in their vibrations class, right? No, we want to do it this way because there are so many tools to help us understand it with RLC circuits, okay? But that's a very insightful question. And Sebastian, I don't quite get your question, sorry. So the indication, are they in parallel, is the V of T placement? Do you mean the velocity of the mass over time? But so I don't quite follow, sorry. Anyway, I know you gotta go. Certainly there's office hours or email. Oh, all right. So have a good evening, everyone. Take care. Bye.
Have a good day.
Yeah, you too.